Welcome to the MRS Bulletin Materials News. My name is Victor Rodriguez-Toro. I'm very pleased today to be talking with Professor Ayse Turak, Associate Professor in the Department of Engineering Physics and the Director for the for Emerging Device Technologies at McMaster University. She's also Associate Member of the School of Biomedical Engineering and of the Department of Material Science and Engineering. Professor Turak is also passionate advocate for materials researchers in the lgbtq plus community. Professor Turak, happy Pride. Thank you for joining me today.
Thank you for the invitation. I'm really excited. I've always been a big fan of the MRS, and so this is an honor for me, really.
Great. So I want to focus our conversation on your work with optoelectronic devices, and more specifically on your group's recent work in the area of nanoparticles and their integration in these devices. Can you tell us a few highlights of this more recent work?
Sure, thanks very much for asking. So we've been working with emerging photovoltaics. So this encompasses sort of the organic semiconductors and perovskite semiconductors. You may have heard of these are the hot topics these days, as well as similar organic and perovskite light-emitting diodes for quite a while, actually. And it's really critical in these kinds of devices, the interfaces at the electrodes, between the different active layers, and even outside the device, all play a critical role in controlling the way that light moves, the way that electrons move. And so this is where we've been focusing most of our work, is tuning the surface properties using nanoparticles that are monodisperse, highly ordered, periodic arrays. And we've developed this very simple, sort of low-cost, scalable approach, which is referred to as reverse micelle templating, to make a wide variety of sort of dielectric, metal oxide, light-emitting, conducting nanoparticles that are size tunable as well as controllable in terms of their spatial organization. And so due to the versatility and tunability of the nanoparticles that we can make, we've been able to, in our group, improve the light management in sort of OLED type devices, improving light emission from white OLEDs, for example, by about 20% by integrating different nanoparticles. We've been able to improve the charge injection and charge sort of balance in these devices, which is really critical for some of these emerging semiconductors that don't act like traditional semiconductors. And we've been able to increase, for example, the efficiency of blue OLEDs. So these are blue emitting, light emitting diodes, by 30% or so, and for OPVs, or organic photovoltaics, by around 20 or 30%. And also this allows us to tune, for example, the degradation, the spatial distribution of degradation in these devices by using nanoparticles strategically. And degradation is a big problem for a lot of these types of devices. So this has been a really hot area for us. The key to the effectiveness that we've discovered, and we just published it last year, is this need for an interlayer that has is sort of a sub-monolayer. So it's less than one complete layer coverage. And when you have that, so we can do that by having our nanoparticles that have different spacings and different sizes. So having this non-uniform coverage of the surface becomes really critical. And what we've seen is that as soon as that's a full layer, the device properties really start to fall off. So it's the key to our ability to control these interfaces is by being able to actually modify how the surface energy is, as well as the surface composition, using different types of nanoparticles. And one really exciting thing that we just published, it was published about 2 weeks ago, so I'm very excited it was finally out, where we used light-emitting perovskite nanoparticles that were matched in their emission spectrum with certain polymer photoactive materials that we use for OPVs. And by having this matching, we were able to improve the performance of those devices, especially in a UV environment. UV is particularly bad for polymer systems, by about 20 or 30%. So we've been able to increase the performance and also block this degradation just by incorporating these light emitting particles that take the unusable portion of the spectrum and turn them into visible light. So these are the sorts of things that we're trying to tackle. So one of the nice things about these nanoparticles is they affect all these different domains: the stability, the light management, and the electronic component. So it's really perfect for optoelectronic devices.
All this sound very exciting. I just want to go a little bit more in depth about what comes next, right? What are What are the applications that you expect these functional nanoparticles in the nanoparticle arrays can impact in the next 5 to 10 years?
Well, there's really a wide variety of domains where functional nanoparticles are emerging as potential options. So obviously in optoelectronics, as we talked about, tuning interfaces, tuning surfaces, but the three most promising areas that I see are really in what we call nanoscale photonics. So these are on-chip lasers, for example, and we've been working hard to try to make our light-emitting materials turn into lasing type materials. So you can really scale down and have everything incorporated on a particular chip, as well as using different kinds of, like taking advantage of the magneto-optic properties of these nanoparticles at the nanoscale to produce on-chip isolators, for example, optical isolators that can act like a valve for light in the same way that we have, sort of magnetic spin valve type materials. Particularly in flexible and wearable optoelectronics, because we're down at the nanoscale, you can take advantage of the fact that we have a very little amount of material, but it has high performance to make really quite flexible and wearable type structures and in sensors. And in the third domain, which is a little bit, it seems kind of a strange area, but really is what I'm going to call disruptive nanomedicine. There's a huge explosion in using nanoparticles, both the inorganic type of nanoparticles that we make, as well as organic nanoparticles for things like drug delivery or for making different kinds of surfaces. You can imagine with COVID, we also pivoted a little bit to looking at some of these things, but we've had a lot of interesting success looking at how nanoparticles on a surface, for example, can make them self-sterilizing. So these are the sorts of emerging approaches that I really see as being sort of the hot things that are happening in the next couple of years.
Great, great. That sounds great. Next, I would like to think, you mentioned wearable electronics, right? And other applications. What do you think are the challenges to using nanoparticles in this kind of devices or applications?
Well, that's a great question. And the biggest challenges are really ones that are more universal. So if we think beyond wearables, one of the biggest problems with nanoparticles is the uniformity of particles and their scalability. So it's relatively easy on the lab scale to make a small amount of nanoparticles that are kind of all uniform in size, but it's really difficult to take that out to commercialization. And an additional problem for wearable type technologies or for flexible technologies is that the substrates have to have these unusual shapes, and they have to be, very, not only very flexible and able to conform to the body or to other parts of things that you're trying to incorporate it in, they also tend to be quite temperature sensitive, because often the kind of things that are able to be flexible or wearable are various kinds of plastic materials, polymer materials. So you need some manufacturing technique that is able to be scalable. So it has to be low cost. It should really ideally be at room temperature. It should be able to cover a variety of form factors. You really need something that makes really high quality, good uniformity, monodispersed, small difference in the diameters of the particles that are easy to make and easy to cover every surface with. And so these things are quite challenging, actually, from a variety of techniques that people use to make nanoparticles.
Yeah, I can imagine. It sounds difficult, yeah, but great. Do you want to add anything else?
Well, I was just going to say that that's one of the benefits of the technique that we've chosen, is that I think you're going to, obviously any researcher would say that their approach is the best approach, but I do think that we've really hit on an approach that allows us to sort of challenge each of these domains. So, it is the technique that we use, which is using diblock copolymer reverse micelles as little like nanobeakers or nanoreactors, where the size of the particle is controlled by which polymer you choose to make these reverse micelles. Basically, it allows us to have this kind of universal approach. And so that's one of the joys of research, is that you stumble upon these things that can help actually challenge some of these problems.
I see. Good. So you have touched a little bit on this, but maybe we can go on in more detail about how the tools that you and your team have developed for the synthesis of nanoparticle arrays can enable the integration in the interface of these devices, and if possible, also in the photoactive layer part, right? for example, in things like solar cells to improve their efficiency. Yeah, any words you have about that would be great to hear.
Absolutely. I mean, so just to expand on what I was saying a little bit earlier, that the the approach that we've taken, because it's based on forming in solution this reverse micelle, and a reverse micelle is basically just a material that has one hydrophilic and one hydrophobic end, this polymer material. So when you put it into a solvent, it immediately forms this macromolecule that we call a micelle. And everybody would be familiar with micelles because that's what soap is, right? So soap basically surrounds a piece of of dirt or something when you put it into let's say on your plate. The polymer, the material that is in a soap surfactant will just surround this material and pull it into solution. And we take advantage of a similar approach, but in kind of the reverse, where we make the inside of our micelle sort of hydrophilic, so it's the sort of water-like, which means that you can do solution chemistry just inside these little beakers. That's why I call them nanoreactors or nanobeakers, because it allows you to have access to this sort of solution chemistry. And the idea there is that if you can do it in solution, or you can do it in any kind of beaker, there's a lot of work that our chemist friends have done in making lots of different reactions possible within an aqueous or even in other kinds of solvents. And once they're in solution, these nanoparticles, you can then print them by a wide variety of techniques. You can cover every surface. You can do it at room temperature. These are the kinds of benefits that the approaches that we've been taking are having, because as I said, it allows us to challenge all three of those domains. You can make highly ordered arrays with uniformity and tunable composition, tunable size, tunable spacing, just by changing a few knobs of our deposition parameters, of which we have many, to get a wide variety of different sort of surfaces. That's one of the beautiful things about this sort of approach. And we've been working very hard recently in trying to incorporate the nanoparticles into sort of more sensitive substrates. So certain substrates that are really sensitive to, say, solvents, or they're sensitive to temperature, or they're sensitive to sort of plasma treatments, or things that are post-processing treatments that we might want to do to improve our particles. If you can't deposit them directly on the surface, we've developed a bunch of sort of transfer printing techniques using graphene or using different polymer layers as sort of sacrificial transfer layers to move the particles from one surface to another. So not only can we deposit it directly by using all the printing techniques, spin coating, dip coating, slot die coating, spray coating, all these things with basically the same size and same organization, but you can also then put it on even more sensitive surfaces or weird looking surfaces where you can't directly deposit it by transferring it using all these different systems. And the beauty of that, of course, is that you can also make interesting composite materials, like having these graphene nanoparticle composites. So not only can we use them to transfer the particles, but also we can take advantage of the sort of grafting of these onto these sacrificial layers to take advantage of them in devices. So these are all various ways that we've been trying to incorporate them into sensitive photoactive type structures where you can't use traditional lithography, you can't use traditional high temperature methods.
Understood. Good. So there are any kind of properties that is expected for the nanoparticles to have? So all these methods that you have described, you have touched on some of those properties, but I don't know if you want to expand a little bit on that aspect, what the particles need to be or what properties they need to have.
Well, for our approach, the most important thing for not the nanoparticles themselves, but to achieve the nanoparticles, is that they have to be somehow processable in solution. So there are some materials that you just can't access from a solution perspective. We basically put everything into a beaker, mix them together, and kind of let nature take its course, right? So you have all these highly these high quality reactions, and as I said, our chemist friends have done a lot of work, and you can really produce metals, you can produce metal oxides, dielectrics, perovskite type materials, like lots of wide variety of different types, conducting nanoparticles, like lots of different material types, as long as you can in the bulk produce them in solution. So as I said, the micelles act like little nanobeakers. And so what's the reason that you're getting nanoparticles is you're just confining spatially the reaction that would happen in the bulk anyway. So there are certain types of reactions that you can't access this way. And so these sorts of particles just require, I won't say that they're impossible, because we've actually been able to develop a couple of techniques where you can encourage more infiltration, or you can change various kinds of the stability of certain particles, or you just use different reagents that are accessible to try to achieve similar structures. But ultimately it comes down to, can you produce this in solution? And then secondarily, can you get it to go inside the micelle so that you're actually taking advantage of this nanobeaker? So once you can answer these two questions, which are not trivial, but there's a lot of possibilities there, you can achieve almost any structure. I like to, when people ask, I always like to say it's not completely universal, but it's almost universal. So if you have a particle that you want, we can try our best to produce it in the way that you need, and usually we're successful in making those types of structures.
Great. So some of your papers highlight a key role that lithium fluoride can play at interfaces in organic optoelectronics based on polymer Fullerene photoactive layers. What might be the potential role of these interfaces, the lithium fluoride interfaces, for high efficiency organic solar cells based on non-Fullerene acceptors or polymers only in the photoactive layers? This is kind of new devices that,
Yeah, this is definitely an area that we've been very interested in for a while now. Lithium fluoride is known to have a very particular type of interaction with fullerenes, and that's why they've been quite successful and incorporated into fullerene type devices. But it has also been shown to have lots of interesting high efficiency structures have been made with other organic molecules. So the most obvious example, I guess, is one of the earliest examples is alq3, which is this, I won't say the chemical name. I'm not a chemist, so I'm a material scientist by training, but not a chemist. So I'm going to skip the long chemical name and just mention it by its abbreviation. But this type of material is sort of an archetypal material, green emitting organic, small molecule organic, that was used in OLEDs even back in the very first devices in the 1980s. And that material also shows high efficiency with when you have a lithium fluoride interlayer. So there's likely to be a lot of promise in these non-fullerene materials, looking at either a lithium fluoride interlayer or possibly another interlayer. Because one of the things, this actually goes way back to the research I did for my PhD, but one of the things that came out of my PhD work ages ago, I won't even mention the years, but was that it's really a holistic system. So it's the electrode material, the interlayer, and the organic all together, the three of them, that act as this high efficiency system. And so once you change the polymer, you do have to start looking to see if there are other materials that might act similarly to the way lithium fluoride does with fullerenes for these non-fullerene materials. But I feel that it's pretty promising that we have seen some success with incorporating lithium fluoride into these non-fullerene structures. Is not as good as with fullerenes. And so my suspicion is that we need to move away from the standard electrode materials. So if you move away from aluminum and into things like silver or gold, as people are starting to do with some of these non-fullerene materials, the interlayer itself will sort of start to have to change. So lithium fluoride is a good starting point, but it really gives us insight into the kinds of structures that are useful at those interfaces. And as I mentioned, we saw that it really comes down to having a submonolayer. And it's not easy to achieve submonolayer structures when you evaporate on top of an organic material. So these are one of the areas that we've really been trying to focus on how do we get these nanoparticles with this submonolayer structure into those devices effectively without losing the spatial organization, so that we can explore, is it the material? Is it the spacing? Does it have to do with something else? So as we move into these non-fullerene materials, we can really target what aspect of the material is allowing that injection, because this has been a hot topic in lithium fluoride research for many years. There's a lot of controversy about what actually happens with lithium fluoride at that interface. And I would say that even now, people don't 100% know why this wide bandgap dielectric material works like this really amazing tunnel junction, right? So these are the sorts of questions that people are still asking. And I think that it's the beauty of a field like organic electronics, where we don't, they are non-traditional semiconductors, so we have to start thinking about them in non-traditional ways. So they go beyond the standard models. And so we need to really get a deep understanding of what's happening to see, okay, what's going to be this target material? Maybe it's lithium fluoride, but my suspicion is that it's probably going to be a different type of material that becomes the optimal interlayer.
Okay, great. So you have spoke, or you have shared the impact of your work in organic-based optoelectronics and perovskite-based optoelectronics. Which type do you think will be preferred for commercialization?
So this is the golden question, right? And I would say that if you had asked me this question, say 2 years ago or 3 years ago, I would have said hands down it's going to be perovskites. Perovskites have taken off with like incredible ferocity. It has impacted so many different domains, beyond even the photovoltaics domain, where currently the the world record certified efficiency for research cell is, I think, is 25%, and silicon is 26%. I mean, we're basically there, right? They're basically there for single junction cells, and and so the incredible processability of perovskites, their really exceptional charge carrier mobilities, all these things, their long carrier lifetimes, all these things. I would have said, as I said 2 or 3 years ago, that they would be the number one choice. And I mean, you see a lot of people are pushing in that area. But these non-fullerene acceptors has really changed the game for OPVs. OPVs 5 years ago, 6 years ago, was verging on being almost a quaint scientific interest, but really no point for commercialization. And a lot of the people who are working in OPVs moved to perovskites actually in those years. But the work that's being done even in the last couple of years on these non-fullerene acceptors has changed the game. Right? So now we're seeing 20%, 21% from organic photovoltaics, which would have been completely impossible. When I was doing my my PhD work, or even my postdoc work, it was we were happy when we got 3 or 4% out of these devices, and to even consider that we go above 10 was the big breakthrough, where people were like, once it reaches 10%, this is going to be a commercially viable technique, because that was the sort of target goal: 10 years, 10% efficiency for a long time. And that the 10 years is still a problem in terms of the device lifetime, but the efficiency barrier is completely shattered now. So I think that there's a lot of work that people have done in the organic realm, and OLEDs are so successful, and there's a lot of crosstalk between these two communities, right? So the light-emitting diode people have really, OLEDs are a game changer in terms of making flat panel displays and things like that. And so those lessons are translating over into OPV, though they had been for many, many years. And so I think that it's going to be a battle. It's going to be a neck and neck battle to see which one ends up being cheaper. At this point, it may be that, well, so I'm gonna prevaricate. I apologize, but I think from the processing and sort of low temperature type approaches, you can deposit them from solution, et cetera, of perovskites makes them really attractive for commercialization. But on the OPV side, there's a lot of infrastructure that's already been established for OLEDs that you can adapt easily, relatively easily, for OPV type production. And so it's kind of looking at the commercialization possibilities, it's sort of is it going to be the economies of scale, or is it going to be the existing infrastructure that sort of wins? I'm not sure. Like a couple of years ago, I would have said for sure it's going to go in one direction. Now the possibilities seem much broader, and that's very exciting. As somebody who grew up in this field, who started in this field relatively early, I'm really excited to see organics develop as much as they have. Like I said, those first years when we had these tiny little devices that were that died after 5 minutes, that could barely, you could see the glow, but they weren't that bright, just to what has become now is really an incredible transformation, within my sort of research lifetime. It's really incredible.
Yeah, it sounds like future is unpredictable, but exciting, right? So,
Oh, well,
yeah,
that's the beauty of science, right? Is that
yeah,
you, you,
good.
you think you know what's to come, and then 5 minutes later something happens that just changes the game. So we'll see.
Yeah, great. Okay, let me switch gears here a little bit to talk about diversity in STEM. As a researcher in the LGBTQ plus community, what has been done that made you feel integrated into the material science community?
So it's a hard question to answer in a little bit, in a way, because I've been very fortunate in all of the places that I've worked. I've been out for most of my career. I was actually, during my PhD years, I was the co-chair of Pride Toronto, which is one of the largest Pride celebrations in Canada, and actually around the world. It's a gigantic undertaking. 1 million people come to Toronto for Pride and things like that. And I thought, hey, I'm in the middle of my PhD. This is a great time to chair this this like gigantic volunteer organization. And it was right around the time that marriage equality came in Canada. So there was actually like a ton of press, and so everybody saw me everywhere. And this was in the middle of my PhD. So my status as an LGBTQ researcher within material science was very well established by everybody knew it, basically, right? And so it was, the communities I was in were always really welcoming, and they always knew about me. They would always incorporate my partner, my my wife now, for example. My colleagues always ask about my wife, all that kind of stuff. But it's more these local communities. I wouldn't say that there's been this massive embracing of diversity within the larger material science or or engineering generally, or science generally fields. In the last couple of years, there has been a little bit more development, but I live in Canada. Canada is a very progressive place when it comes to LGBTQ rights, and yet at McMaster, for example, I think I'm the only out professor in engineering, for example, and one of only a handful at the whole university. And so it just tells you that even in these cultures that are technically very, very open and very welcoming, and like I said, my own colleagues, my local community, everybody is fantastic, but there isn't this broader acknowledgement, or I mean, somehow people don't feel comfortable enough, even in such a supportive environment. I've always found it very supportive to be open and to be out. I heard a story of a colleague who, in engineering, at a different university, not at my university, but at a different university in Canada, who, he got married to his husband, but didn't really tell any of his colleagues, didn't feel comfortable sharing that information, came to work directly from his wedding, kind of like, it was really, he didn't feel like in that environment it was possible to even talk about this home life that he had, and he was very private about it. And I mean, I don't face any kind of overt discrimination that I can feel, but there is a culture where, people are always like, oh, there's always this heterosexist assumption that, they're like, who's your husband? What's going on? Do you have kids? All this, the kind of questions that people ask are very pointed in a way that kind of forces you to come out. And if you feel comfortable doing that, and I mean, like I said, I was the chair of Pride Toronto, so I was like the most out lesbian in Canada for a long time. And so I never felt that there was any point in being closeted, because, you could just Google me for a number of years and you would get pages and pages of information about me, my partner, everything, all that kind of stuff. But for people who aren't as high profile, let's say, it's harder for them to face with that question, to say, oh yeah, it was me and my husband, or me and my wife, or whatever. And I think that's the biggest challenge. So it's a weird way to answer this question, is that I've always felt included in in all the places that I've worked with. My colleagues have been really amazing, but overall, the culture is still one where people feel very, very closeted, and they have a lot of difficulty. I've had a number of students who have come out to me in the course of my teaching career, both as a TA and as a professor. But mostly they're very quiet about it, right? They tell me, they tell certain people, but it's not a known thing within the class, within these areas, And I think that kind of thing really speaks to the fact that, we make lots of progress, but there are still societal sort of expectations of people that when you step outside of those boundaries can really make it difficult,
Good. Thanks for sharing these stories with us. In this direction, what can institutions like universities or research centers do for researchers, especially those coming from backgrounds that represent diversity in STEM, to reach the best technical and personal version of themselves?
Well, I do think that things like this, like what the MRS Bulletin is doing, highlighting people and talking about various things around LGBTQ issues is a way to make a difference. I think being open and talking about it is the way to sort of move forward. I think one of the big things that I would like to see is to highlight these things not during Pride, like during June, you see lots of them. You see all these spotlights or these showcases or that kind of thing. But at other times of the year, that part of your identity is not is not discussed or thought about or brought into focus. And the same thing goes with, for example, Black History Month, right? Like during Black History Month, there's lots of celebration of of people of color and different kinds of especially in the US, African American type scientists and things like that. They all of a sudden are showcased, but then the rest of the year, nobody talks about them, right? And so I think those are the kinds of things that can go a long way in normalizing the fact that people, all of these what we consider underrepresented groups in STEM, have always been there. They're always there, and they may be visible, they may be invisible, but they've always been there, and we should celebrate them all the time. Right, and celebrate the contributions of people constantly rather than erasing them. I think that one of the things that people, this is a controversial statement in a way, maybe, is that there's there's always a desire to sort of mainstream certain people and downplay the what diversity brings. It's like, these engineers are just like us, is sort of the mentality that was around for a long time, especially when I was in my undergrad. There's like a standard male culture of engineering, and the idea was that if you are like us, then you can be one of us, sort of thing. And I think right now there's more of an understanding that an engineer can take all different forms. And in fact, we need all these different perspectives and all these different ways of looking at the world and ways to solve problems in order to actually achieve change within a technical problem or within societal problems. An engineer's main role in life, I feel, is to provide a service to society, right? Like this is why in Canada, for example, we have the Iron Ring. It's to remind you that you have a particular obligation to society to make things better. And if we're really going to challenge the problems that we face, we need different perspectives. We need people who come at problems differently. There's been this understanding that if you're going to solve a problem, you often need different disciplines. You need people who have civil engineering backgrounds and chemical engineering backgrounds and material science and electrical to, say, make a robot, for example, right? That digs tunnels. You need all these different domains to solve a problem like that. But beyond just looking at disciplinary, like eroding disciplinary silos, I think you need to also think about having people who come from different backgrounds, who have different perspectives, who look at problems differently, that allows us now to achieve the kind of success that you wouldn't get if it was a monoculture, right? If everybody is the same kind of engineer and they have the same mindset and they have the same approach to problems, then we're going to solve the same problems, right? And in the same way. And then that won't lead to innovation. That won't lead to the sort of solutions that we need to the kind of wide-ranging problems that require inputs from all sorts of people. So I think those are the things that I would like to see celebrated more that diversity itself is really the goal, I think, as an engineer, is to have as many viewpoints, as many people around the table, as many people, as many stakeholders giving their perspective. And you can only do that if you open the doors to these people.
Great. Thank you for sharing those thoughts. And as we go to the last part of our conversation, I would like to kindly ask you for an advice for the new generations of researchers, right? Coming from different backgrounds that represent diversity in STEM. Anything you want to share with them?
I think the advice that I would have for people is that if you're bringing your whole self to a problem, then you can have success, right? And so, it's important to think about these spaces that you're moving into as spaces that you belong in, right? You don't have to change yourself to fit into these spaces. These spaces are here for you, actually. And I would say that if you're interested in a career in STEM, 100%, there is space for you here. This is a space where you can exist. And the more of us there are, the safer it becomes. One has to always make sure to protect themselves and not put themselves in a position where, they're like, just because I think I belong here, maybe other people have different ideas. But I think you can always find those spaces, and you should seek out those other people. And there are great resources out there. For example, at McMaster, we have a great group called Engiqueers that was established, sadly, only a couple of years ago, but is a group of queer engineers who are banding together to make a safe space for other people who don't fit the traditional, perspective that people have in the heterosexist view of what an engineer should be. And those kind of spaces exist, I think, in every engineering school, probably within many types of companies, that kind of thing. But I guess my other piece of advice is don't compromise yourself for a job, right? Like if this environment that you're in, the STEM environment that you're in, is not one that allows you to be your authentic self, then they don't deserve to have you, and you deserve better than that. So I think those would be my key pieces of advice.
Professor Turak, thank you very much for your time. It has been a pleasure to talk to you, and hopefully we can meet in person.
I hope so. Thank you very much for this opportunity.
My name is Victor Rodriguez-Toro from the Materials Research Society. For more news, please visit the MRS Bulletin website at mrsbulletin.org. And you can also follow us on Twitter at MRS Bulletin. Thank you for listening.